Recording started.
Oh, welcome to lecture 4.8, which are applications of the trigonometric functions. I'm by myself here this afternoon, but hopefully I'll explain things well enough for everyone to understand, since I don't have my usual suspects in the room telling me if everything was clear or not. This particular section is going to go pretty quickly because it's really just synthesizing the knowledge that we've built up over the past chapter, really, but mainly from 4.5 and onward. So without further ado, I'll move forward. Okay, so the objectives for this section are to be able to solve a right triangle, and then we're going to do a couple type of application problems, some involving bearings, and I'll explain that later in the lecture, and some problems involving simple harmonic motion. And I'll pre-apologize for any coughing or sneezing that happens. I've been sick for the past few days, and I've given 2 lectures today already, so hopefully my voice will hold out for us. Okay, so we begin this particular section with talking about what it means to solve a right triangle. And in short, solving a right triangle means knowing all of the measurements of the 3 interior angles and knowing all of the side lengths of the right triangle. And when I say know, I rather should say we find all of the side lengths and all of the interior angle measurements. And we can do this using sine, cosine, and tangent functions. There is a particular problem that we're going to look at that I'm actually going to use the Pythagorean theorem. And so just different methods that we know of to associate the sides of a triangle and the angles of a triangle, of a right triangle, that is. Okay, so we start with this right triangle here pictured. Notice we always label our angles with uppercase letters, and the side lengths are identified with lowercase letters. So also notice that the side opposite the angle corresponds alphabetically. So across from angle A is side A, and so on. Let me just take this off of there because I want a clean triangle to begin with. And let me get a different colored pen and a little bit thicker. Okay, so we're told a couple pieces of information here. We're told that angle A is equal to 62.7 degrees. Well, I already know that angle C, since it is a right angle, is 90 degrees. And really, we never label that. It's understood with the symbol being there showing it's a right angle, that it's understood that it's a 90-degree angle. So I still need to find angle B, or the measurement of angle B here. And I'm given side length A. I'm just going to try to keep these color coordinated here. So side length A is listed as 8.4, and we'll just say units It could be inches, feet, whatever you're measuring in. I'm just going to put 8.4. Now, if they had given a specific measurement type, I would definitely want to label it properly, but we are just given generally 8.4 there. So this is all the given information that we have. So we still need to find angle B. We need to find the length of the hypotenuse, side C, and the length of side B. So we will start out with angle B. We have two angles of the interior, so it's not that difficult to find the third angle. And the interior angles of a triangle sum to 180 degrees. And if we take out the right angle, if we take out that 90 degrees, we're left over with 90 degrees. So to figure out what angle B is, I simply need to know that angle A plus angle B has to be 90 degrees. Well, I know the measurement of angle A, which is 62.7, plus angle B equals 90 degrees. I'm going to subtract 62.7 degrees off of each side of this equation. And I get that angle B is equal to 27.3 degrees. So I have found all of the interior measurements of the interior angles here. Now I just need to move to my side lengths. And let me remind you of our mnemonic device that helps us remember how the sides of the triangle relate to the trigonometric functions. We have SOH, CA, TOA, which is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And right now, if I look, I'm trying to get side B here. Well, I know that if I took the tangent of angle B, that would be giving me the opposite, which is side B, over the adjacent, which is side A, that I know. And since I know two of the three pieces of information, it's a very simple equation to solve here. So let me set it up. Once again, I know that the tangent of angle B has got to be equal to side B divided by side A. So that is opposite over adjacent. So the tangent of, and I know the measurement of B, 27.3, has to equal side B divided by the length of side A, 8.4. And so now I just do some inverse operations here. I multiply both sides by 8.4 to get that 8.4 out of the denominator on the right-hand side. And I'm left with 8.4 times the tangent of 27.3, and that's degrees, equals the length of side B. So I put this into my calculator. One thing you want to make sure that you've done, since we're dealing in degrees, you need to make sure that your calculator is in the mode of degree and not radian. And to do that, you just press the mode button. In that list, you can either toggle back and forth between radians and degrees. Make sure it's set on degrees or you will not get the correct answer here. And when I put all of this into my calculator, I find that side B is approximately, and it says to round to 2 decimal places, I get 4.34. So what I have found out in regards to solving my triangle is that side B is equal to 4.34. Now all I have left is the hypotenuse, and I could certainly use these trig functions just like I used here to find side B length. I could use trig functions to find side C, but I would assume that most of you are very familiar with the quadratic formula. I'm sorry, not the quadratic formula, the Pythagorean theorem. So I'm going to use the Pythagorean theorem since I have 2 of the sides. Very simple to find the third side. So the Pythagorean theorem states that, let me get my black pen here, a squared plus b squared is c squared. And a squared in this case is 8.4 squared plus 4.34 squared equals c squared. And when I square 8.4, I get 70.56. And when I square 4.34, I get 18.835.6, and that equals c squared. When I add those together and take the square root, I did this earlier on my paper and I forgot to write down, and I don't have my calculator in my hand. It looks like about 89 point something there when you add those together. But I would add those together, and then I am going to take the square root of both sides, and I get that side C is approximately 9.45. Pardon me. So I have all 3 side lengths and all 3 angle measures. This right triangle is considered solved. Pardon me. Oh, I forgot to take the answers off. Actually, let me do this. Hide them from you for a moment at least. Oops. There we go. Like magic. Okay, and let me get my pen back. All right, so we're given a problem here regarding the Eiffel Tower, and it says from a point on level ground, 80 feet from the base of the Eiffel Tower, so right here, the angle of elevation is 85.4 degrees. And they're asking us to approximate the height of the Eiffel Tower. In other words, find the side length of A, and we want to round that to the nearest foot. Now, if I have this angle here, we'll just call it angle A since it's opposite side A there. And I start thinking about the trig function, so toa. And I want to use the trig function that will relate my opposite side and my adjacent side, because A is opposite angle A and the 80-foot side is adjacent to angle A. So it looks like tangent would be my best option. Now, you can certainly use any of the trig functions that would involve the 80-foot side and angle A, since those are the pieces of information that you know, but I figure that it'd be quickest to use the tangent since I'm looking for side A specifically there. So I have that the tangent of 85.4 degrees is equal to the opposite, which is side A, over the adjacent, which is 80. And so this one solves, this particular equation solves very much like the last one we did. I'm going to multiply both sides by 80 to get that out of the denominator on the right-hand side. And then I'm just going to put 8 times the tangent of 85.4 into my calculator, and I get that side A is approximately, I'm rounding to the nearest foot, 994 feet tall. And I can label this properly by putting feet. Moving forward. Okay, so we have another application problem having us use our method of solving a right triangle to find the answer. A guy wire, which is just one of the wires that comes off of an electrical pole or a telephone pole. I think mainly an electricity pole, electrical pole. But it's the wire that comes off and attaches down at the ground. That's what a guy wire is. So a guy wire is 13.8 yards long and is attached from the ground to a pole 6.7 yards above the ground. Find the angle to the nearest tenth of a degree that the wire makes with the ground. So we're talking about this angle right here. If this is side A, that would be angle A there. So I have the situation, let me give you our little mnemonic, SOHCAHTOA. I have the situation that I want to find that angle measure by relating my opposite side with my hypotenuse. So I know that the sine of angle A is equal to opposite 6.7 divided by hypotenuse 13.8. However, I can't just multiply both sides by something to solve this because the angle A here is contained within the sine function. So I have to go back to the material I learned, I believe in 4.7 regarding reciprocal functions. I'm sorry, not reciprocal functions, inverse functions. In that, let's see, let me write it up here. The sine of theta equals some value, we'll say x, and this is if and only if the inverse sine of x is theta. So I can use inverse sine here to undo the sine function around the angle A that I'm trying to figure out. So because the sine of A is equal to 6.7 over 13.8, the inverse sine of 6.7 over 13.8 has to equal angle A. And once again, you just simply use your calculator. You have the second function on the sine key as your inverse sine function. And when we put the left-hand side of this equation into our calculator, we end up getting, and we're rounding to the nearest tenth of a degree, we end up getting 29.0 degrees. Now, I do have to put the 0.0 to show that I have rounded to the 10th place. And that's it for that one. Okay, so I was actually pretty excited to see this next section come up when I was preparing the notes for this lecture, because I have seen the notations that we're about to talk about, probably more times than I can count, but I never knew what they meant. And so I was excited to learn something new about bearings. So in navigation and surveying problems, the term bearing is used to specify the location of one point relative to another. The bearing from point O to point P, and I'll show you this O and P here in a moment on the next slide, is the acute angle measured in degrees between ray OP and a north-south line. The north-south line and the east-west line intersect at right angles. So it's going to look a lot like our X and Y axes. Each bearing has three parts. It has a letter, north or south, the measure of an acute angle, and a letter E or W, which hopefully it jumps out at you that is for north, south, east, and west. So these next few problems are going to go very quickly once you understand what that definition of bearings was just saying. So if the acute angle is measured from the north side, so I'm talking about this side of the north-south line, then we write an N first. So let me just give you an example of a ray that would qualify for that. So let's say we have a ray coming out here, and welcome Mesha, and this is point O at the origin, and then there's a point P on the ray going out. We measure the angle from the north-south line. So my angle would be measured from the north side of the north-south line, and we'll say that's 40 degrees. So you're going to have three indications for your bearings. The first is what side of the north-south line is the ray being measured from. So in this case, it's being measured from the north side. It is a 40-degree angle from the north side of the north-south line. So that's the second part. The second part, we write the measurement of the acute angle. The third part is to tell which side, left or right, or east or west of the north-south line the angle is being measured to. So it may be difficult to see, but I did put directional indicators on here. So let me just make this bigger. There's an N there, north, south, east, west. So this particular line, or ray, is coming off of the north side of the north-south line. It is an acute 40-degree angle that is measured to the east side. So the bearings for this point P would be given as N 40 E for north, 40 degrees east. We'll move on to, and the other two that we have to look at, like this, or three actually, are just as simple. It's basically just looking at it and using descriptives in the form of symbols to tell where it is located. Okay, so Maisha, I didn't ask you on that last one since you had just come into the room, and I wanted to give you a chance to catch your breath, but was that description making sense to you? You can either give me a green check or a red X. And you can access the green check or the red X. And okay, there's right above your name, the name panel, there's a smiley face, there's a guy with a clock, there's a hand, and then there's a box with a check in it. The box with the check in it is a drop-down menu that'll either let you give me a green check or a red X. There you go, I see your green check. So I will go ahead and we'll look at this next example here. And you found the emoticons, I see. All right, so let's take this as an example. I'm going to draw a ray starting at the origin here out into the third quadrant. Here's my point P and my origin O. And remember, the angle is always measured from the north-south line. So I'm talking about this angle here. And we'll say that's a 65-degree angle. So if I want to give the bearings for that particular point, or I'm sorry, angle there, position, if you will, I would say, okay, you know, I've got three spaces that I need to fill here. I need to tell which side of the north-south line it's on, so it's on the north side. It is a 65-degree angle, which is always measured from the north-south line. So you don't have to worry if I'm talking about, let me get a different color. You don't have to worry if I'm talking about this angle here, because you would never measure when you're talking about bearings. You'd never measure from the east-west. You always measure from the north-south. So north, 65, and then I want to tell which side of the east-west line I'm lying on, and that would be, obviously, the west. So N65W is how you would give the bearings for that particular position. You good, Maisha? Great. And so one more example here. Let's take a fourth quadrant example. So I'll draw a ray here. I have my origin O and some point P on my ray. And since I always measure from the north-south line, I'll be talking about this angle here. And we'll say that that angle is 70 degrees. So if I want to give the bearings for this position, it would be S for the south side of the north-south line, 70 degrees, and it's moving to the east. Okay, so let's look at an example problem with this type of thing. Okay, so uh-oh, I forgot to erase the answers on this one too. That's what I get for stealing the PowerPoints from the publisher. All right. Okay, so we're given this diagram here off to the right. Notice that we haven't necessarily been given the correct angles because all of the angles that we would talk about with bearings would be measured from the north-south line. So the first question asks us, the bearing from O, the origin here, to D. So D is right here. So the bearing from O to D, point D is located to the south and to the east of the north-south line. And the angle that I'll be using is, of course, the one measured from the north-south line, so that's the 25-degree angle. So if I want to state the bearings for this particular, or for the position from O to D, I would say, okay, that's on the south side of the north-south line. It's 25 degrees, and it moves to the east. Easy enough, huh? And then the next one asks us to do OC. Maisha says, yes, it's easy. I know for once. I was going through this lesson. I'm like, this lesson's going to feel like kindergarten to them after everything else they've been studying this chapter. So this next one is OC. Now, if you notice, we don't have the measurement that we need right in there because it's always got to be measured from the north-south line. And Maisha, I see you're typing something, so I'll keep an eye out to see what you have to say. What we do know is that from west to south is a 90-degree angle. That's the third quadrant there. And we know that the angle on this side is 75 degrees. So that means that little angle in there has to be 90 minus 75, which is 15 degrees. So now we're ready to give the bearings. It's on the south side of the north-south line, and that's a 15-degree angle, and it's moving to the west. So south 15 degrees west. Maisha, are you ready to move forward? Or I see that you're still typing something, so I don't want to move forward if you have a question about this. Okay, so that's a green check. All right, I will move forward then. Okay, so this is the last type of application problem that we'll look at for this, not only this section, but this chapter, this is the last material before you're ready to take your test over this material. So, simple harmonic motion. What we're told here is that an object that moves on a coordinate axis is in simple harmonic motion if the distance from the origin, D, so they're calling that distance D, at any time is given by either a cosine or a sine function. And just to remind you of what that looks like graphically speaking, I need to move that up. so I can show the amplitude. Okay. So remember, cosine coasts down. That's how we can remember the difference. So cosine starts at 1 above the x-axis, and it coasts down to -1, and then back up to 1, and so on. And then we have sine that starts at the origin, and it is the exact opposite. It comes up, and then down, and then up. So what this definition is saying is that any movement of an object that follows one of these functions is considered to have simple harmonic motion. The motion has amplitude, so we've already encountered that word, and that is the description here is maximum displacement of the object from its rest position. So the rest position in either case here would be considered the x-axis there. So the amplitude is that distance that it varies either above or below from the resting position. Meisha, does that description of the amplitude, along with the picture there, does that make sense? Okay, good. I'm glad that was clear. I felt like I was rambling there for a minute. Okay, and the period of the motions is given by this little formula here, where omega has got to be greater than 0 because you can't divide by 0, and we don't want negative values. The period is how we describe the time it takes for the motion to go through one complete cycle. So if we were looking at the cosine function, we would be talking about the time it takes to go from there all the way back up to its starting position. So that's one period there. All right, so in describing simple harmonic motion, the equation with the cosine function, d equals a cosine omega t, is used if the object is at its greatest distance from the rest position. So let me break that down. If we're talking about the cosine function, we're talking about starting an object from its greatest distance in regards to the resting position. That's why we choose the cosine function, because the cosine function starts up away from the resting position, whereas the sine function, let me get a different colored pen here, whereas the sine function is used when the object begins at its rest position. So notice the sine function goes right there, or begins right there at the origin. So hopefully that makes sense as to when you're going to know to use either the cosine, so that's when the object is at its greatest distance or begins at its greatest distance away from the resting position, or sine function when it begins at its resting position. And your t is your time. Okay, so let's look at a couple of problems involving harmonic motion. So we have a ball is on a spring. A ball on a spring is pulled 6 inches below its rest position, and then it's released. So we're talking about starting away from the resting position. So you should already have bells and whistles going off in your head that we're going to be looking at D equals A cosine omega T. Yes, yay, cosine. I see you typed it down there, Meisha. Excellent. And the period for the motion is 4 seconds. So remember, the period is that time it takes to cycle through once. And we want to write the equation for the ball's simple harmonic motion. So we have a time of 0, and we have a distance of 6, since we're 6 inches below the resting position. That means since we're 6 inches below the resting position, that 6 is serving as our amplitude. And actually the D is -6 since it's below the rest position. But when we find amplitude, we take the absolute value, so that's why your amplitude is always a positive value, because we're talking about a quantity, not a direction once we talk about amplitude. But the D is -6 since it's resting below the rest position, or since it's pulled below the rest position. And so we're going to use the equation. We already wrote it at the top. D equals A cosine omega T. I think that's omega. I should probably look that up again. The funny looking W, that's what we'll call it. Whatever that is in Greek. Apparently it's not that big of a concern to me to know my Greek alphabet anymore. It's been a while. Okay, so just to remind you, we have D equals A cosine, funny W, T. All right, so the absolute value of A is the maximum displacement, also known as the amplitude. Because the ball is initially below the rest position, A is equal to -6. The value of funny W can be found using the formula for the period. We were told on the last page that the formula for the period is given by 2 pi over funny W. And we also know on the last page we were told that the period was 4. Remember, it took 4 seconds for it to cycle through. So I know at this point that I can set 2 pi over funny looking W equal to 4. And now all I need to do is period equals pi over 2. Okay, that is the period for, I think it's cosine. So we're talking about a specific formula for the harmonic motion. That's why it's different. Is that okay, Meisha? Yeah. So yeah, we're dealing with a specific formula for this phenomenon of harmonic motion there. Okay, so and here, I can go back and let you see that slide real quick. Hang on just a second. Let me expand my little, if it'll let me. Come on, give me something to grab onto here. I want to make sure that, okay, here we go. Let me go back a couple slides. Okay, so if you see right here, let me get a different color pen. We're told in regards to harmonic motion that the period is 2 pi over funny W there. Okay, so going back. And let me go back one more. We're also told here that the period is 4. Okay. Now we're ready to move on. So we've got the period, 2 pi over funny W is 4. So now I just need to solve for funny W. And to do that, I need to get that funny W out of the denominator. So I'm going to multiply both sides by funny W. And those divide out. So now I have 2 pi equals 4 times funny W, and divide 4 off of both sides. And I get funny W is equal to, well, I can reduce that fraction there. 2 goes into 2 once and into 4 twice. So I end up with, oh, maybe that's what you were saying. You had already worked it out. Pi over 2, had you already worked that out, Maisha? Is that what you were telling me? Oh, brilliant, brilliant. I thought you were referring back to when we were in like a couple lessons ago when we, you're so right. I thought you were referring to like what is the period for cosine? I'm sorry for the confusion there. That's awesome that you had it that quickly. You were way ahead of me on that one, girl. Okay, let's move forward now that we have our period. So we have our, I'm sorry, not our period, we have our funny W, and that's pi over 2. And we know that our A is -6. So all we have to do now is write the equation. So I'm going to move to the next slide. I think I've got room on the next slide to write it. Okay, so here's my information here that I know. So the equation, once again, the form we're following is D equals A cosine funny WT. So for this particular situation specifically, I have D equals -6 cosine of pi over 2t. So there we go. We have harmonic motion equals -6 times the cosine of pi over 2 times the time that it's been in motion. Good deal. I didn't even have to ask. Excellent. We've got one more problem to look at. Okay, so simple harmonic motion, either given by this cosine or this sine, and it has a frequency given by, it's just the opposite of the period, and notice the frequency is defined as the inverse of the period. So notice it's the reciprocal or the inverse of, I'm sorry, reciprocal, not inverse. It's the reciprocal of the period there. Remember, the period was given by 2 pi over funny W, and the frequency is given by funny W over 2 pi. Okay, so an object moves in simple harmonic motion is described by this equation here, where t is measured in seconds and d in centimeters. Find the maximum displacement. So the max displacement, remember, that's basically the amplitude. And that sits in the position of A in our equation there. So the maximum displacement is 12, and this is given in centimeters. So 12 centimeters is our maximum displacement. Okay, so the same equation here. This time they're asking for the frequency. Well, we know the frequency is equal to funny W over 2 pi. Funny W sits in the position here as the coefficient of the t there, the t term. Actually, it's not a term. Yeah, it's a term. The coefficient of t. So let's go ahead and plug in what we know. So this has got to be equal to that, let me change colors, the pi over 4, and that's being divided by the 2 pi from the formula. So let me point this out. This is really 2 pi over 1, and the reason I did that is because I'm about to divide fractions, and whenever I work with fractions, I like everything to look like a fraction. And I never divide fractions, I multiply by the reciprocal. So now I have pi over 4, not divided by 2 pi, but multiplied by the reciprocal 1 over 2 pi. My pi's divide out, and I'm left with a frequency. When you multiply fractions, you multiply straight across. I'm left with a frequency of 1/8 cycles. Yes, ma'am, I see your 1/8 down there. Brilliant. Cycles per second. Well, if we have 1/8 of a cycle per second, you may be able just to reason that it's going to take 8 seconds to get through one cycle, but I'll show you how to find it algebraically. Let's move to the next slide. Okay, so to find the time is equal to 2 pi over funny W. Remember, that's our period, the time it takes to move through that cycle. So 2 pi divided by funny W is pi over 4. And I'm sure you're about to slap that up there before I can get done, Maisha. So go for it whenever you get it. So I have 2 pi over 1 divided by pi over 4, which is the same thing as 2 pi over 1 times the reciprocal, 4 over pi. My pi's divide out, and I get 8 seconds. So it should make sense that if it took, yes ma'am, you got it. It should make sense that if I can do 1/8 of a cycle, not fast enough. If I can do 1/8 of a cycle in 1 second, then it would take 8 seconds to make a full cycle. So that's all I have for you today, Meisha. Do you have any questions about anything we covered here?